So in this part of the lecture, we are going to look at a few examples on the use of the Bernoulli equation, which we recall along a streamline. It states that P plus half rho V squared plus rho G times Z is a constant, where P is static pressure, rho is fluid density, V is velocity, G is acceleration due to gravity, and Z is elevation, height. Okay, height from a chosen plane of reference. And we are basically going to see examples on how to use this. Okay, so if it's not clear at the moment, hopefully it will be clearer soon. And this comes with the assumptions that the flow is steady, partial derivative with respect to time is 0, flow is incompressible, which means density is independent of pressure or a constant, and that the shear stress or the viscous effects are 0, so tau is 0. Okay, so we define an arbitrary streamline. What the statement says is this is true for all the points on the same streamline. So if you consider any 2 points, you can apply the Bernoulli equation. If you consider any point, it must add up to a constant, which is true for that particular streamline. For a different streamline, it will be a different constant. And just for the sake of completeness, we also write along the normal direction at any given point on the streamline, the pressure variation in the normal direction plus rho V squared over n plus rho G times partial Z over partial n is 0. We will use this equation less frequently, but I will definitely go through some examples which make use of this equation. So this is the information you need to solve problems, and we are going to start by looking at a flow situation of that of a tank. Okay, we are thinking about a tank here. We are thinking about a tank which is given in figure 3.11. Okay, looking at figure 3.11. Okay, and we have the tank. We have a like a hole at the bottom where the fluid is going to discharge, and initially let's say the height of the tank is of h. Okay, we'll call this plane z equals 0. So this would be z equals h. Okay, and I'm going to say this plane here, we want to calculate what is the velocity with which fluid leaves the tank from the bottom. So if you have a tank here, fluid discharges because gravity acts down. Obviously, gravity acts down. At the top surface, we can assume that the fluid is at rest. Okay, it's moving ever so gently, or that you are talking about modeling the discharge for the first few instances after the bottom cap is opened. Assuming that there is a bottom cap and you open it, what is going to be the velocity with which the fluid leaves the bottom in the first few instances? That's what we are going to calculate. So if you think about a point 1 here, you would assume that the flow is steady. The fluid is, let's say, water, which is incompressible. And that we ignore viscous effects. So we just say that the fluid is moving only due to gravity and the pressure difference. We don't talk about viscosity yet. Okay, so we say the flow is inviscid. So these are my symbols: steady, incompressible, inviscid flow. And I choose point 1 here and I assume that the flow is along streamlines, so I am going to have it flow up to point 2, okay, and I am going to apply, and I am going to think there are going to be several streamlines like these, something like that, okay. I am going to choose an arbitrary streamline and try to apply the Bernoulli equation between point 1 and point 2. So at point 1, what do I have? I'll call this pressure P1, and I'll call this pressure P2. P1 plus half rho V1 squared plus rho g Z1 equals P2 plus half rho V2 squared plus rho g Z2. Okay. I do know that at the top surface the fluid is almost it's at rest. It's just starting to flow. So V1 is 0. V1 is 0. Okay. I want to solve for V2. That's what I am interested in. That's the quantity that I am seeking. Okay. And the fluid here, okay, if you think that the pressure here is P1, it's the same fluid at the bottom. It is also discharging to the atmosphere. So this is also the atmosphere, and so is this. So P1 equals P2 equals the atmospheric pressure. Okay. So if I throw in these simplifications here, I can strike out P1 and P2. V1 is 0. So what I have is half rho V2 squared is rho g times Z1 minus Z2. What is the height of level 1 minus the height of level 0? That would be equal to h. So this is rho g h, or V2 is square root of 2gh. I should add it is approximately equal to, because we did add a lot of simplifying assumptions, and V2 is given by the Bernoulli equation only for the first few instances after the bottom cap is removed. That is, if you want to know what is the velocity with which it will jet out, once it starts jetting out, obviously the liquid level will drop, and you can't assume that this is h. So you need an equation or a time dependent h, and this makes the flow unsteady by definition. So this analysis will only serve you in the first few instances, and it is incorrect to think that it is applicable for the entire time it takes for the liquid to discharge out. Okay, so that will violate the steady flow assumption. So this is a simple example where we derived the velocity of the fluid at the bottom, and in all such problems the key to your solution is that you identify 2 points that are on the same streamline. So I'll write identify 2 points on the same streamline at least one. You should know the pressure, velocity and elevation to solve for the conditions the other. That's it. This one sentence, if you understand how to use the equation, you can solve problems. If I choose 1 and 2, I need to know the velocity at 2. So I choose 1 where the velocity is 0. And I know the pressure at both ends, so I eliminate that. And then I try to solve for V2. So we'll similarly try more examples. And one more example that is seen in figure 3.15 is that of a syringe. We look at the example of a syringe. Okay, a syringe is something that has a wider cross section and a plunger, and you have liquid here that you push through, and it goes through a very narrower cross section. And let's say this cross section here, or this cylinder has a diameter D1, and we'll assume this has a diameter D2. Okay, if I tell you that I push the plunger with a velocity V1, that is the liquid in this that is in contact with the plunger, if it is moving with a velocity V1, okay, I want to know what is the velocity with which the fluid that is exiting the syringe will move. I'll call it V2, and I need to solve for what is V2. Okay, so as usual, we are going to assume that the plunger is being pushed in a steady manner, steady flow. The fluid inside is some kind of a liquid which is incompressible, or some kind of a fluid that's incompressible, and we ignore all viscous effects and call this an inviscid flow. Okay, so I'll take a point right down the center. I'll take a point at the center. I'll call this 1. Call this 2. I'll apply Bernoulli equation between 2 points. I am identifying 2 points on the same streamline for which I know the conditions. Okay. So what I am going to write is the same equation, P1 plus half rho V1 squared plus rho g Z1 equals the other, and I am going to say they are at the same elevation. They are at the same elevation, so we don't have to worry about the term Z1 equals Z2, or we'll just drop rho gC is not important. It's not changing. Okay, so first simplification is there is no elevation involved. Okay, so I can strike out these two terms. V1 is known, and we have to solve for V2. We have to solve for V2. And P1, the pressure at point 1 and the pressure at point 2, we are just going to assume P1 equals P2 equal to the pressure of the liquid. Okay. So with these assumptions, if I write, half rho V1 squared equals half rho V2 squared. Sorry, I shouldn't assume this P1 equals P2. I should just say P1 plus half rho V1 squared equals P2 plus half rho V2 squared. Okay, this is by applying the momentum balance or force balance, which is Bernoulli equation. The other balance that I can apply is if I take a section here and if I take a section here, I have to conserve mass, that is the density times area times velocity must be conserved. This is mass balance. So what I have is the velocity at section 2 is the velocity at section 1 times the ratio of area, which is equal to the velocity at section 1 times the ratio of diameter squared. Okay. Now P2 is discharging to the atmosphere. Okay. P2 is discharging to the atmosphere, so I'll call P2 equals P1, and I can write V2 is V1 times d1 over d2 whole square. So I can take the Bernoulli equation P1 plus half rho V1 squared equals P2, which is the atmospheric pressure, plus half rho, instead of V2, I'm going to write V1 squared times d1 over d2 the whole square. So I can write P1 minus P atmosphere is equal to half rho V1 squared times d1 over d2 the whole squared minus 1. Okay. Yes, with this equation and the area ratio, you can get V2, that is the exit velocity. You can get that. V1, the plunger velocity, is something that you can control because you press that with your finger. You can control the plunger velocity, so V1 can be controlled. Okay, and it is discharging to the atmosphere, which means you can figure out what is the pressure at the surface where the plunger and the fluid are in contact. You can solve for that. P1 minus P atmosphere, I'll call this P1 gauge. This is half rho V1 squared times d1 over d2 the whole squared minus 1. So these are the two quantities that we solve. One, the exit velocity using mass balance, and the pressure at section 1 using the Bernoulli equation. Okay.